block diagram reduction technique in control system. First of all, we will see what is block diagram reduction. In control system, block diagram is used as a graphical representation of a system, and it gives the functional relationship among the components present in the system. So each block represents a mathematical operation performed by the particular block, or it can be called as a transfer function, and the arrow given in between the block diagram represents the direction of signal flow. So in practical system, the block diagram is often a very complex one, and it may consist of many interconnected blocks. So in order to analyze the system, we have to determine the overall transfer function. The transfer function is nothing but it will give the input-output relationship in the system. So in order to get the overall transfer function of the system, we have to reduce the block diagram, or we have to simplify the block diagram. So this process is called as block diagram reduction. Next we are going to see what is the need for block diagram reduction. So usually the block diagram consists of multiple blocks. So as I have already told you, we have to convert this multiple block to a single block so that it will give the overall transfer function of the system. So in order to analyze the system, we need to find out the transfer function of the system. So the main objective of block diagram reduction is to get the transfer function of the given system. Next we are going to see how we are going to reduce the block diagram. So in order to reduce the block diagram, we have to follow various reduction techniques, or we can say we have to follow various rules for it. So we will see one by one in this presentation, and finally we will see an example. So this is the first rule, that is combining blocks which are in cascade or in parallel. So this rule gives information or how we can reduce the block which are arranged in series or in parallel. If you take the first diagram here, there are two blocks which have the gain factor of G1 and G2, and these two blocks are arranged in series. Okay. So if you want to reduce the blocks which are in series, what we have to do means we have to multiply the gain inside the block. So what is the output means, finally we are converting these two blocks into a single block with a gain of G1 and G2. So if two blocks are in series, we have to multiply the gain present inside the blocks. And the second diagram represents the parallel connection. Here two blocks are connected in parallel, and this symbol represents the summer. Okay, here in this line we are getting a gain of G1, and in this line we are getting a gain of G2. Okay, and at this point we are adding the two gain G1 and G2. So what will be the final answer means G1, and the final output from this block diagram is G1 plus G2. So how we can, if these two blocks are connected in parallel, we can make it as a single block with the gain of G1 plus G2. So from this, what we can understand is, if two blocks are connected in series, we have to multiply the gain present in the blocks, and if two blocks are connected in parallel, we have to add the gain presented in the blocks. So this is the first rule. Next we move on to the second rule. Here we are going to move the summing point behind a block. So in this diagram we are having a block and a summing point. Okay. So now I am going to shift this summing point behind the block. So why we are doing so means, see, usually the control system is represented in a complex block diagram. So if you know this reduction technique, we can easily reduce the block diagram and we can easily find out the overall transfer function of the system. Okay. So in this case, how we can move the summing point behind the block means, here see what is the output we will be getting is, see, whatever the output we are getting after the summing point is multiplied with the gain G. Okay. Suppose if you are moving the summing point behind the block, so whatever the point we are summing up with the summing point will not be multiplied with the G. So whenever we are shifting the point, we have to multiply this branch with a gain factor of G, so that we will get the same output as that of the previous one. So I will explain with another block diagram so that we can easily understand. Here, see, this is the summing point and we are having a block here with the gain of G. So at this summing point, you will be getting a output of A plus B, because both the input are get summed in the summing point. So you will be getting the output of A plus B. So this output is multiplied with the gain of G, so that you will be getting a final output of A plus B into G. So whenever we are shifting the summing point ahead of the block, at that time also you have to get the same output. So how can we get this? So in this case, I have moved the summing point ahead of the block. At this point, I will be getting the output as A into G. And if I put directly the B, I am connecting the B input to this point, I won't get the gain factor. So what I have to do means, I have to include the another block which consists of the gain G, that should be multiplied with the input B, so that at this point I will be getting the output as A plus B into G. Okay. So whenever we are moving the summing point ahead of the block, that each branch should be multiplied with the gain G, so that you will get the same output. Similarly, in the next rule, we are going to move the summing point ahead of your block. Okay. So in this case, let me explain with an example. So here, in this case, I am going to move the block move the summing point before the block. So here also, this line has the input A and it will be multiplied with the gain G, so that I am getting an output AG. And at this point I am having the input as B. So the final output what I am getting as an output is AG plus B. So whenever I am shifting the summing point before the block, I should get the same output like AG plus B. So in this case, I have shifted the summing point before the block. Okay. Suppose if I did it, if I directly connect the B point to the summing point, So here the input is A, right? So what I will get is A plus B the whole multiplied by G. But this is not my expected output because I should get AG plus B. So how can I get means only A should be multiplied with G but not B. So what I am trying to do means I am going to add another block with the B input with a gain of 1 by G. So at this point I will be getting the output B by G. So here I am getting A and here B by G. So whenever I multiplied with the gain G, the final output what I am getting is AG plus B. So whenever we are shifting, the one branch should be multiplied with the inverse of the gain. Okay. So the next rule is moving a pick-off point behind a block. So here what we are going to do is I am going to take this branch behind the block. Okay. So for this what I have to do means I am going to multiply, I am going to include a block with the gain factor of 1 by G. Why I am doing this means, see, suppose if this is the input, I am giving an input as A, at this point also I will get the input as A. But at this point my output will be A into G. Okay. So here A. So at this point I will be getting A into G, but if I didn't add this block and directly if I have taken the output, at this point also I will be getting A into G, but originally I should get the output as A. So I am adding a block with gain factor of 1 by G, so that if I multiply AG with 1 by G, this G get cancelled, so I will get only A here. So in order to move a pick-off point behind a block, the pick-off point should be multiplied with the inverse gain, that is 1 by G. Similarly, moving a pick-off point ahead of a block. Okay. So in this case, suppose if I take this input as A and here I will get the output as AG, and here also I will get the output as AG. Suppose I want to shift the pick-off point ahead of the block, and suppose I didn't add this gain factor, what is the output I may get? Consider this is the input A. So at this point I will be getting an output of AG similar to the before one, but here I may get only A, but I have to get A into AG. So what I am going to do means I have to multiply this pick-off point with the gain G, so that I will here also I will get the output as G. Okay. In that way we have to follow the rules to reduce the block diagram, and this is very important rule, that is eliminating a feedback loop. So in this case, so here we are having a feedback path with the gain H, and you may get both positive or negative feedback, so that here we have represented as plus or minus. So suppose if you want to reduce this feedback path, you have to follow this rule or you have to use this formula. We have considered the whole feedback system. We are going to convert this whole feedback loop or feedback system to a single block diagram with the transfer function. So if you are reducing this feedback path, you have to give this transfer function that is called G1 divided by minus or plus GH. That means if you are having a positive feedback system, you have to put negative symbol here. Suppose if you are having a negative feedback system, here you have to put positive. So G divided by 1 plus or minus GH. Depending upon the feedback loop, we have to apply the formula. And in the second case, here we have a unity feedback system. What is unity feedback system means? The feedback path has gain of value 1. So in this case, as like that of the previous formula, in the place of h we have to put the value of 1. So it will gives the formula as G divided by 1 plus or minus G. And the final rule is wrapping with two adjacent summing point. So suppose here there are wrapping means exchanging. So here there are two summing points. So we can wrap the two adjacent summing point like this. So no need to give any changes, as like that you can change the summing point. So this is the 7th rule. So these are the basic rules we have to apply to reduce the block diagram. So now we can see an example to find the overall transfer function from this block diagram by applying various rules. So here we are going to determine the overall transfer function of the given system. So this given system is represented as a block diagram. So here the C of S is output and R of S is input. In between we are having an interconnected blocks with different gains. So in order to find the transfer function, we should find C of S divided by R of S. We will see step by step. So this is the given system. So in the first step, what I am going to do means I am going to shift this pickoff point to the left hand side of the block. So you can see here I have shifted this point to here. So under that condition, as we have already told, we have, in order to shift the pickoff point before the block diagram, we have to multiply the branch with that gain G4. So I have taken out this block here, but at the same time this pickoff point is multiplied with G4. So this is our first step. So the remaining all blocks are same as that of the previous one. So in the next case, what I am going to do means I am going to reduce this feedback path. I am going to reduce this feedback. So this is one feedback path. So I am going to reduce this feedback path, and this is a negative feedback path. So we have to apply the corresponding formula. So after applying the corresponding feedback reduction formula, so this feedback path is reduced to a single block with the gain of G3 divided by 1 plus G4 H1 G3. Okay, the remaining blocks will be same. as that of the previous one. So what is our next step is, so again this whole block will form a feedback path, again a negative feedback path. So we can reduce this negative feedback path by applying the corresponding formula. So that is, the corresponding formula is G divided by 1 plus GH. So that is why here we are getting plus symbol. For negative feedback path we have to put plus symbol here. So I have reduced it. So you can make these two block as a single block. How means? So these two are in series, in cascade. So you can multiply G2 G3 divided by 1 plus G4 H1 G3. Okay. So this is the function going to present in the single box. So now this block and this block are feedback path. So you have to apply the negative feedback formula, so that it will be reduced like this. So this function, this whole function is taken as g of s. So g of s divided by 1 plus g of s h of s. Instead of h of s, here we are having h2 here. So in the place of h we have to put h2. So this block is reduced like this, and the remaining blocks are same as that of the previous one. And in the next step we can reduce these two blocks, because this block and these blocks are in series. So what we can do, if both the blocks are in cascade, we have to multiply the gain present in the block. So here we are going to multiply the gain. So this will become G1 into this function G2 G3 divided by 1 plus G4 H1 G3 divided by 1 plus G2 G3 H2 divided by 1 plus G4 H1 G3. So we can reduce these two into a single block. So you will be getting the block like this, and I have taken LCM so that it will become a single function like this. Now obviously from this diagram you can see that this is again form a negative feedback path. So again you have to apply the rule, negative feedback formula. Okay. So what we can do means, so this whole function is nothing but g, right? So which formula we can use is 1 g divided by 1 plus gh. So in the feedback part we are having the gain g4. So we have to use the negative feedback formula, so that we will be getting a single block as it is. So finally we have reduced to a single block, and this G4 is present here as it is. So these two blocks are now in series. So what we can do is, we can multiply the gain present in each block. So after taking LCM, this block gives the function like this. So in the numerator we are having G1, G2, G3, and in the denominator we will be having 1 plus G3, G4, H1 plus G2, G3, H2 plus G1, G2, G3 and G4. So which is in series with another block having gain of G4. So we can multiply these two gain to get the final transfer function. So the C of s divided by R of s equal to, finally you have to multiply this G of 4 with this gain, so that we will be getting G1, G2, G3, G4 divided by 1 plus G3, G4, H1 plus G2, G3, H2 plus G1, G2, G3 and G4. So this is the final transfer function. So we have converted a complex block diagram of a system into an transfer function. By this you can easily analyze the system. So in order to get the transfer function easily, you have to apply block diagram reduction technique. So this block diagram reduction technique is essential for control system analysis, and in order to get it we have to apply various rules. You can apply cascade, parallel, feedback and the shifting of pick-off points, like that. According to the system you can apply different rules. So in the previous example we have applied only pick-off point rule as well as the feedback path rule and the series connected rule. So similarly, for more complex problems, we have to apply a different rule in order to get the final transfer function. So what is the main goal of this block diagram reduction is, we are going to get a single transfer function representation for the given control system. Thank you.